as per Indian Standard Code 800 2007. So this is going to be Unit 3 if you are studying in Savitribai Phule Pune University uh, in Maharashtra. And let us start with this. So beam column, what is beam column? The first thing is, so a beam column is a member in a steel structure which is subjected to both bending plus axial load. So, or you can say compressive load. So the one which the member which carries both bending moment, you can write in this way, and the axial load P. So this member is nothing but we call it as a beam column. A beam is a member which is subjected to bending or maybe the bending moment in terms of forces, and the column is a member which is subjected to axial load or P. So the one which carries both is nothing but the beam column, or these are beam column is nothing but the columns which have uh, um, which are designed for uh, sustaining the bending moments as well. So, for example, in a building, this is a plan of a building I'm drawing, and this has maybe, let us say, this many columns. So, this is one column, second, third, fourth. This is how the columns. So, this column, mm, yeah. So, this column is going to be this column is having load from here, 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 and here. So this column actually having a bending moment from this side, bending moment from this side. These both are equal spans, therefore they're cancelling each other. Bending moment on this side and bending moment on this side because of these two beams, but they are of same span, so they are cancelling each other. So effective bending moment is zero at this column, and there is only an axial force B. Therefore, this is column. This is just a column. But if you see this column is having bending moment because of this beam and this beam, which is cancelling each other. So no bending moment on this side, but on this axis, if you see, there is one bending moment because of this, but there is nothing to counteract this one. So it has a bending moment in this direction plus axial load P. So this is called as this this column is nothing but your you this is for uniaxial bending. So but it is a beam column definitely. And this column, if you see this corner column, it has bending moment on this side as well and this side as well. So this is a biaxial. This is having a biaxial moment, but this is also beam column. Okay. So yes, my dear friends. So this is what is the concept of beam column. So let us start with the uh, steps to design beam column. So steps as per IS800 2007. So you have to go for the clause number 9.3 in the IS800 2007. So the step one will be your given data always. So in this video we'll be looking only for the steps, and the next video will be looking for a problem, one design problem. So you will be given with a P, that is your applied axial load in kilonewton. Okay, if it is, let us say this is working load, and then you will be given the bending moment. Okay, that will be kilonewton meter. Uh, let's say these are the working uh, load and bending moment. So your step 2 will be, or you can start with the step 1 from this step as well. So what you will do is you will write the fact, you will factor the load, factored P, nothing but PU is equal to 1.5 P, and same you do for MU. So factor bending moment will be MU 1.5 M. So the first step will be factoring the loads if they are not factored. Then the step 3 is, now you go, this is a design of a section. So you will go for a trial section. So you need to find a trial section. So what will be the trial section? How will you find the trial section? So basically, we find the trial section based on, uh, we decide some trial section based on the axial load which is acting P, PU. Based on this, we just ignore the EMU for uh, defining or try for selecting a trial section. So what we do is, the basic equation. Always remember, stress is equal to force upon your area. Force is nothing but your compressive force upon the area of cross section. So what we want to find is actually area of cross section. So, and what is your stress here is at CD, if compressive design compressive strength. So design compressive strength is nothing but your sigma, and P is nothing but your PU, and A is your area required. So AE required is nothing but your, if you say PU upon FCD. So what you actually do is, here you multiply this area by 2. Why? Because you are only considering PU as your, for selecting the trial section, you are ignoring MU. To counter or to minus the ignored MU, we multiply this equation by 2, the area by 2, and we find the area. So, okay, now in this step you get some E required in EMN square. So then you go to your steel table, find a section which is having somewhere around this area. This comes around, let us say this comes around 300 mm square. Then go find a section or I section which is essentially having area greater than or equal to 300 mm square. Okay, so that's how you select, and then what you do next step is your step 4. Once you select the section, always always, but this area should be uh, okay. Then then what you do is the classify the section, classify the section. How you classify the section using table 2? You know how to use the table 2. We can check that in our problem when we solve the problem. Then your step 5 comes, uh, find the buckling class of the section, buckling class of the section. Okay, and then your step 6. What is your step 6? So your step 6 comes to find uh, design axial load, okay, that we call as ND. And this equation, if you go to um, clause, so now if you go to your IS code page number 70, you can find here the equation of ND written somewhere here. If you see, the ND equation is written as ND is equal to AG F1 upon gamma m0. Whenever you're solving a beam column problem, please try to go in the section 9.3 where we are discussing the member subjected to combined forces, section 9, and in that section 9 you go to the combined axial force and bending moment section, and then here you see the equation. This is our real equation which we are going to use at the final, but we are at this step where we are calculating ND. ND is the design strength and tension, okay, and the ND is AGF upon gamma m0. So you write here ND is equal to, here you can write design strength in tension, and then you can say okay, ND is equal to AG F1 upon gamma m0. So what is your AG? AG, you know, AG is your A provided or which you for the section which you have chosen, and then Fy you know will be 250 megapascal, and gamma m0 is 1.10. Okay, so you get Nd here in kilonewton. Then step 7, design strength in bending. Go for design strength in bending, and the equation for design strength in bending is given by clause 8.2.1.2, which is clause 8.2.1.2. So you need to go in the IS code and in the page number. Here, so the page number is here. Your yes, page number is somewhere around 53. So you get this equation MD is equal to beta BZP Fy upon gamma m0 8.2.1.2. So your MD is equal to beta B Z Fy upon gamma m0, where your beta B, what is your beta B value? If you go to IS code again, the beta B value is 1 for plastic and compact section, and if you have semi-compact section, then you go for ZD upon ZP. So everything is given in the IS code. Beta B is equal to 1 for plastic and compact section. When how do you know if it is plastic or compact? In step 5, we have checked the buckling class of section, and if it is semi-compact, then you write your beta B as ZE upon ZP. The values of ZE and ZP you can find in um, I can write it here. Can be found in Annex H of IS800 2007. Okay, then you can find the ZP value from there. Then you get Fy, 250 MPa, and gamma m0 is equal to 1.10. So that's how you find your MD. You get some value in kilonewton meter, and that's how then your final step for the problem, step 6, is check for strength, and this equation you can find in clause 9.3.1.1. I can show you the equation here. Yeah, so this is the equation which I highlighted just few moments ago. that n. So n here is nothing but your PU upon ND. So this n is your PU, ND is what we have found, that uh, design strength in tension plus. Now I told you that if the beam is uniaxial, then you have only one M. If you have two M's, if it is biaxial, if it is a biaxial one, then you have My and Mz or X. But it is, if it is uniaxial, then you only have one My or Mz, whatever you call it. So it's just a thing, and in the given question you have given with only one moment, so Mu upon Md should be less than or equal to 1.0. That's how your equation, and I can take this equation and write it here. So Pu, I can write in this form first, M upon Nd, M upon Md should be less than or equal to 1.0. That's how in our terms we write it, P Nd plus Mu upon Md should be less than or equal to 1.0, and this comes out to be less than equal to 1. Then therefore, okay, and save. And this much are the test steps for the solving the beam column problem. Thank you for watching.